a very brief preview on fluidized catalytic cracking. Now, this is one technology which has changed the way refining is done in the last 70 years. And so in this session, we will talk about what is catalytic cracking, why do we do it to begin with, what are the major equipments that we use. The heart of the FCC technology is the reactor regenerator section. Now, this is one area that I would definitely would like you to learn because at some stage or the other in your career, you would actually have to do something or the other with this particular technology. And also, the catalyst that is used, the various additives that are used, and how we regenerate the catalyst. It's a very different technology as compared to what you have learned so far. Unit heat balance, pressure and process variables. As usual, I told you that before I begin a new technology, I try to get your bearing in terms of where actually this technology belongs in the refinery, configuration. And as you already know, fluidized catalytic cracking actually cracks very heavy molecules, which is virtually the bottom of the barrel and otherwise useless. In fact, in 1860s, 1870s, 1880s, when crude oil was discovered, this particular stuff was considered as waste. And what people used was basically the kerosene, which replaced shale oil to burn, lanterns and for lighting homes. But this particular technology, as you can see, can crack heavy atmospheric gas oil called HAGO, light vacuum gas oil, even heavy vacuum gas oil. So basically, all the products from the vacuum distillation column, which are otherwise called what we call as waxy distillates, and belonging to carbon number virtually from C25 to anywhere to C60. These kind of carbon numbers, we don't really have any use in day-to-day life, excepting if you can separate wax out of it. So this is sent into a fluidized catalytic cracking unit, which actually uses a catalyst to crack these heavier molecules to lighter molecules, like, for example, ethylene, propylene, C4, C1, C2, C3, C4, naphtha, and also diesel. So we get actually our day-to-day products out of the FCC unit. And as we go along, I'll actually also explain why FCC is becoming more and more important and assuming more significance as we actually initiate our transition from oil to chemicals, and to be able to reduce the production of gasoline and diesel. Now, I must tell you that fluidized catalytic cracking is actually a gasoline machine. In other words, in a refinery, if you want to make large quantities of gasoline, FCC manufactures that, because as you can see, this is the FCC gasoline which goes into the blending pool. And both the isomerate as well as the reformate help to actually reduce the sulfur in the FCC gasoline to meet the final spec, as well as dilute the olefin content, which is there in the FCC gasoline. But nonetheless, as I'll explain later on, as we go along, even we have learned how to actually to reduce, if not eliminate, FCC gasoline from the FCC unit. So it is one of the most important conversion processes in our industry today. It is primarily used to convert high boiling, high molecular weight hydrocarbons, as I mentioned. And it's actually the major workhorse of a refinery. If you ask me, the typical margin that you get in a refinery, it could be anywhere from $1 to $2 a barrel to something like $13–14 a barrel. This kind of a margin, the essential contribution into this margin or the profit is from the fluidized catalytic cracking unit. And essentially, it is a true marvel of engineering. And actually, as once we are done in discussing FCC unit, you'll also understand and appreciate the kind of engineering interventions which have gone in to make FCC a successful commercial technology. But this does not happen overnight. In fact, it has a long history. In fact, the first very attempt was carried out in way back in 1912, almost 100 years ago, where scientists tried to reduce the molecular mass of heavy petroleum products. Around 1920, French scientist McAfee introduced aluminum chloride as a catalyst in a batch cracking process to crack these heavier hydrocarbons. As you know, aluminum chloride is a highly acidic material, and you need acidity in terms of cracking the heavier molecules. So he virtually carried out, a kind of a Friedel-Crafts reaction to crack these heavier molecules, and this technology continued and to be used for almost like 14 years in the Gulf refining, a company in Port Arthur in the US. Eugene Houdry, another French scientist, he actually came up with what is called as Houdry process. In fact, if you look at some of the old literature in our industry, there's a very classic book written by UOP. The title of the book is Ideas on Rent. I would encourage all of you and then you can download that book from the internet. If you can read that book, it is very interesting the way actually the oil industry grew up. And Eugene Houdry and his son actually developed and commercialized this technology. This is actually one of the first patents that were taken in the hydrocarbon industry. And he actually, used natural clay in 1936, and then the clay was replaced by more active and selective silica alumina. And then in 1942, the major breakthrough happened. And as you can see, a large amount of this activity was carried out during the World War II to be able to provide gasoline and diesel to the war machines of those times. And 1942, basically, although the World War ended, but in fact, the pressure for producing more gasoline and diesel due to World War II actually helped to accelerate the development of fluidized catalytic of this particular technology, resulting into the first commercial technology of what we know today, called fluidized catalytic cracking, which was commissioned in the Esso refinery in Baton Rouge in Louisiana. And this was using powdered clay catalyst. And then in 43, the first moving bed. This was still a kind of a slow moving bed. And this particular technology, although it took birth in 1940s and late 1930s, has actually gone through, as I would say, several births in terms of, re-innovating itself to actually meet the demands of those days, of any day. And to begin with, it was thermofoil catalytic cracking. Then the amorphous catalyst, that is the silica alumina, was replaced by a crystalline catalyst called zeolite. And that actually revolutionized. This was the first major revolution in terms of the yields and the product properties coming out of the FCC unit. And that zeolite catalyst was actually replaced by ultra stable zeolite catalyst. And then in early 80s and late 70s came the riser cracking. And I'll explain all of this, so don't get worried. So I'll explain what is riser cracking. And then many additives actually got in terms of platinum-based promoters, nickel passivators, and so on and so forth. And as we speak today, this particular technology is still evolving in terms of making it much, much more efficient and to be able to make more money. In fact, in our country, you'll be quite surprised to know that the first FCC technology was commercialized by Shell in Chembur in Mumbai way back in 1954. and that unit is still operating there. It is called, in their terminology, it is called CCU, and they also installed a 1 million ton per annum UOP FCC unit later on in early 80s. But in 1954, and if you calculate, it's almost 68 years now that we have been operating that unit. And then immediately after Shell commercialized their technology in their refinery in Mumbai, which is now called Bharat Petroleum, SO, who operated a refinery in Mumbai and Vizag, actually put Exxon Model 4 unit there, SO Model 4. And those two units are also operating even today. So there are three units of the 1950 era that got installed in India as well, and they're still operating. Okay, and they're still making money, and they're all converted from bed cracking to riser cracking. This picture gives you some idea about. You remember I told you about the Eugene Howdrey fixed bed process, 1923. So this is the photograph of those reactors, the fixed bed reactors of Howdrey process. And if you look at the schematic, basically these were huge reactors, as you can see from this picture. You can see that these are pretty huge reactors filled with clay, and you have feed going in and then being cracked, and the products coming out. And once the catalyst gets cooked up, and that cooks up pretty fast, they used to take out that reactor offline and then put air to burn off the catalyst. So it was pretty, time consuming and, very difficult process to operate. Nonetheless, because of the pressures of World War II, this particular technology did make a lot of money. And then the products are, of course, taken into a kind of a distillation column where you separate the light petroleum gas, the LPG, the liquefied petroleum gas, the jet fuel, the motor naphtha, and so on and so forth. So this is the flow sheet of the Howdrey process. The earliest fluidized catalytic cracking, that was the invention by SO, is described here, where you actually take the feed through the furnace and then into the reactor. This is actually a kind of a reactor filled up with the catalyst and operating in a fluidized bed mode. This is just fluidized, not actually continuous fluidization. So this particular catalyst is kind of in a fluidized mode, not in a fixed bed mode. And then the reactor gases go out, and then you put it into a cyclone to collect the catalyst back, while actually the gases go into the main fractionator, into a distillation column, while the catalyst actually then gets sucked along with the air into the regenerator, where actually you burn off the carbon, and this is again in the fluidized bed mode, and you take off the flue gases out and recirculate the catalyst back. So this was the first time that the industry learned how to actually move around a kind of a powdered material between reactor and the regenerator. I actually brought a sample of the catalyst yesterday from our laboratories, and I'll show you if there is an opportunity today. Otherwise, I'll definitely show you next time. I'll physically show you the catalyst so you'll appreciate what kind of material it is. In fact, I will try to do it if I can do it today itself. And this is the picture of, the Baton Rouge refinery Model 1 unit, which was invented by SO, now called Exxon. And so this is the Model 1 unit, and these are the two Model 2 units. And of course, they have been now replaced by more modern technology, which has been developed by what is called Exxon Mobil now. I remember I have already told you about, the analogy of the FCC with a cat, both in terms of 9 lives. I do not know how many lives FCC has gone through, but essentially it is still evolving as we speak. And as we will see later on, Like if you throw the cat, if you toss the cat upside down, it will still land on its 4 feet. Similarly, the FCC unit, whatever disturbance happens, it will always stabilize to a new steady state. So, and you'll see that. I mean, we will discuss it and I will explain that how it happens. So, this is just a kind of a summary of the historical perspective. In 1940s, early 1940s, this technology got developed, what we could today call it as fluidized catalytic cracking process. Essentially, it revolves around two equipments, the reactor and the regenerator. So this is actually the heart of the process, the diagram that you see on the right, and we will actually deep dive into this as we go along in terms of how we design these units. They got feed coming in, and the feed mixes with the catalyst, and then it rises up the hollow pipe called the riser, where the catalyst separates out and the gases go out into the column next. The catalyst actually, after it gets stripped out of the hydrocarbons, it goes into the regenerator, where you blow air to burn the carbon, and then the hot catalyst actually goes back into the riser to continue its journey. So this is the configuration of a typical FCC unit of today. So as I explained to you, 1936 to 1941 was the era where none of this happened. It was the fixed bed, the picture that you saw earlier. Then 41 to 60 was like a moving bed, like the type that we learned in the CCR reformer. 1942 till today, it is fluidized bed. And I mean, I must tell you that when we talk about fluidized bed, there are two kinds of scenario. There are two types of configurations people understand. Like for example, the CCU, the catalytic cracking unit, which came up, which was installed by Shell way back in 1954 at Bharat Petroleum, what is it used to be called as Burma Shell at that time. That actually did not. It had a big reactor where the catalyst was in a fluidized state. But today we don't do that. We actually put the catalyst through a riser. Mm, and I'll come back to that in a moment. End of 45, we had 33 units in operation. In fact, as we speak today, there are more than 450 such FCC units in operation worldwide. In our own country, we have more than 15 such units. Um, Again, the smallest and the largest. The smallest is 1 million ton per annum unit operating in many of our public sector refineries like BPCL, HPCL, Indian Oil. While the world's largest FCC unit is operating in Reliance, 11 million ton per annum, or 220,000 barrels per day. And there are two such FCC units in Jamnagar in Reliance. Each one of them is 11 million tons per annum, that is 220,000 barrels per day. These are by far the world's largest. In fact, the second largest is only about 6 million tons. So, as an Indian, you should be proud to know that we have beaten the rest of the world by a big margin. The biggest is 6.5, not more than 7 million tons per annum, but we have installed 11 million ton, not one, but two of them. And actually today, as we speak from 1955, this fluidized bed system has been replaced by a short contact riser reactor. And I will explain this particular mechanism in a moment. But just to compare actually the two, and I'll come back to that slide. So let me first explain, and then I will come back to that slide. But before I do that, just to give you an idea, like what are the feeds this particular technology can handle. It can actually go anywhere from, as I said, vacuum gas oil to hydrotreated vacuum gas oil, hydrocracker bottoms, coker gas oil, deasphalted oil, even vacuum residue. Okay. So in reduced crude oil, or what we call as atmospheric residue. So basically, almost anything and everything can be processed as a feed to the FCC unit. We have even processed light cracked naphtha, okay, from the coker naphtha. And the products are essentially you get some fuel gas, which is we call as a dry gas, hydrogen C1, C2. You get LPG, and I'll tell you what is the composition of this LPG that we get. And there's a reason why I want to actually spend more time on this LPG. This is a very valuable LPG as compared to straighten LPG that you get from crude oil. Then the light naphtha and the heavy naphtha put together, it is like C5 to 220 cut. This is basically gasoline, which is high octane coming from the FCC unit. Light cycle oil, which is like diesel component, 220 to 370. Anything heavier, which is actually uncracked material, which actually find its place into a fuel oil pool. So in this technology, the conversion that we understand is actually defined as feed minus LCO minus CLO. So the heavy portion, if you subtract from the feed and divide it by the feed, that is the conversion. So in essentially, it is actually the sum total of dry gas, LPG, LCN, and HCN. One more product is there which you cannot see here is the coke, which actually gets laid down on the catalyst and gets burnt off. So actually, if you ever try to do a material balance on the FCC unit in terms of feed coming in 1 million ton per annum, let's say, and the products going out, you will find that the products are roughly 6 to 7% less as compared to what goes in. Because 6 to 7% of the feed in terms of coke gets deposited on the catalyst and gets burnt in the regenerator. And that's how it actually provides the endothermicity. It actually provides the heat to overtake the endothermicity in the reactor. These are the typical feeds that, this particular slide shows typically four feeds, A, B, C, D. A and B are like vacuum distillates, and C is the residue, while D is the hydrotreated vacuum residue. So you can see that there is a difference in the density. The density is a very important parameter for us in FCC, both density and UOPK. The lower the density and the higher the UOPK, the better the feed is in terms of its crackability in the FCC. In other words, the lesser the density, the more is the hydrogen to carbon ratio, right? And higher the UOPK, the more is the hydrogen to carbon ratio. So higher hydrogen to carbon ratio, in other words, more paraffinic material is actually ideal for cracking in FCC. And that is why vacuum gas oil, which has significant quantity of wax, is actually an ideal feedstock for cracking in an FCC unit. In fact, the other parameter, the condensate carbon residue, the CCR, is also a very important parameter because actually higher the CCR, more will be the carbon that will get laid down on the catalyst. And that actually results into high temperature in the regenerators and actually resulting into less conversion, etc. And I'll explain the role of CCR later on. But higher CCR means you would also have metals along with it. So basically nickel and vanadium, these are the two most important metals in the feed that we actually keep track of and keep an eye on. In fact, it is, the FCC unit has a window of operation. The y-axis of that window is CCR and the x-axis is the nickel plus vanadium. It is, nickel plus 4 vanadium, Ni plus 4A. And this particular window of operation, it is where actually the operators try to actually operate the FCC within that window. In other words, higher nickel and vanadium or higher CCR can actually affect your catalyst and make the process more expensive to operate. As you can see, actually, the 95% point also is like in residue, it is much higher. So actually, if you process a light distillate, like for example, B, you get higher yields of olefins, higher yields of LPG, higher yield of gasoline, and vice versa. And this is the typical, for example, these two distillates that I showed you, A and B. A is a heavier distillate, B is a lighter distillate. you can see that the yields are quite different here. Like for example, you get more gasoline here. This is C5 160, more gasoline, both light and heavy. You get extra quantity of propylene for 3.6 to 3.9, etc. But before I compare A and B, let me explain this data to you in terms of the product that we get. You do get some H2S because there is sulfur in the feed, and this cracking reaction does produce hydrogen and methane. But what is valuable is ethylene. You get C2 component, out of which ethylene is valuable, because of the in fact, in a large FCC unit like the one that we have in Jamnagar in Reliance, there is actually, although this number shows 2%, but still in an FCC unit of capacity like 11 million ton, these numbers can be serious numbers, and therefore one can cover this ethylene in Jamnagar. We actually ethylene and ethylene to polyethylene, etc. You can see that unlike straight-run LPG, this propane, this C3 component contains propylene, and today actually, if people want to make propylene at a very low cost, particularly to make polypropylene, fluidized catalytic cracking is a technology of choice because it converts a very low value material like a vacuum gas oil into a pretty high value material like propylene. And even the C4 fractions have olefins like, for example, isobutene and isobutylene actually. So you have, one butene, two butene, two cis-butene, two trans-butene, etc., etc. And each of these molecules have value actually to like these normal butenes. So these are values for distillates. They are much higher, and you can see the coke yield is low for the lighter distillate. In fact, the heavier components also gets reduced. So this is the typical yields that you get. In fact, if you deep dive into the type of gasoline that you make, this is for actually distillate B. This data. So for the light gasoline and for the heavy gasoline, these are the typical densities. We fractionate the gasoline, and you can see that the octane is pretty high. The light gasoline is about 94 octane, while the heavy gasoline is 92 octane. Aromatics is pretty high, and I'll come back to this aromatics part later. And the life cycle oil, which is basically one thing that you must see is that there is significant quantity of olefins here. So if you blend this gasoline into the gasoline pool, and if the olefin limit is 18%, you need to have diluents like reformate and isomerate to actually dilute the olefin in the FCC gasoline. So unlike what we have seen so far, like reformate or isomerate, this particular gasoline blending component has olefins in it. And the heavier you go, that means as you go up on carbon number in FCC gasoline, the olefin content goes down, but the aromatics goes up. And similarly, for LCO, which is actually our diesel fraction, everything is fine in terms of clog point, pour point. It has some good cold properties, but the cetane number is low. And if suppose in a refinery there is sufficient quantity of straight run diesel of high cetane number like 51, 52, you could blend some part of this LCO in that diesel. But otherwise, it becomes difficult because this low cetane number is not advisable, and you cannot meet the cetane index, cetane number specification on diesel if you blend LCO. And that is precisely because of the high aromatic content, around 80%. So what we do in Jamnagar, because we do have very large quantities of LCO being produced because of the high capacity of FCC, we actually take it into a hydrocracker and hydrocrack the LCO to be able to produce again LPG, gasoline, and high quality diesel. And then the bottom end, which is called as a slurry oil, that is actually an uncracked material, or basically material coming which is essentially uncracked at pretty high density, 1.0, 1.025, slightly more than water. and this actually ends up in the fuel oil pool, more or less. So this is actually the kind of a breakup of products that you see, and where actually people make money from these products is basically the propylene, because you can then convert that to propylene, the isobutylene from which you can make MTBE, methyl tertiary butyl ether. We actually make butyl rubber in our refinery in Jamnagar, and halobutyl rubber, which is used in tubeless tires. This is the first time India, otherwise the entire requirement of India is imported. So this is the first time India started making butyl rubber using a Russian technology. And so these C4 components are pretty valuable, and of course the gasoline as well. And I'll talk about how in future we can reduce this gasoline production from the FCC units. Um, I think one idea you could have got by now is that if we can develop a technology to recover these aromatics from the FCC gasoline, then we can actually recycle the rest of it back into the cracker to crack further, while we make pretty high quality aromatics, which is benzene, toluene, xyl. Um, as far as the FCC process as such is concerned, it is distributed into 5 sections. The reactor regenerator section, which is the heart of the process, the flue gas treatment section, which is actually the flue gas coming out of the regenerator, the main fractionator, which separates out broadly these components like the gas oil, the gasoline, and the LCO, HCO. And then the gas concentration unit. The main fractionator and the gas concentration unit actually handle the reactor products, the reactor off gases, and fractionate them into the various products that you just saw. And finally, the catalyst handling system. So to begin with, let me actually talk about the reactor regenerator section. I'll come back to this particular material later. So this is actually the heart of the process, and this is how it works. So what we do is that the hot catalyst, which is coming from the regenerator, this is the regenerator, this is the riser, this is the reactor. The reactor consists of two portions. One is the riser, and the other is the reactor body itself. And so basically, the catalyst, which is coming from the regenerator, this is pretty hot. This is almost having a temperature of something of the order of 680, 690 degrees Celsius, around 700 degrees Celsius. And that comes and actually we inject feed here, the LVGO and the HVGO. We put steam at the bottom to keep this catalyst in a fluidized state. So actually, as it comes through, it meets the feed and it vaporizes the feed. When the feed vaporizes, it carries, it creates huge amount of gases, which help to actually carry the catalyst through, which is what is called as a fast fluidization or continuous fluidization. So you must have studied, fluidization in your undergraduate classes, and I will actually explain this later on. But if you have a peg bed and you start putting air through it, at some moment actually the packed bed, the material in the packed bed will get carried along with the air. And that is what is called as fast fluidization or continuous fluidization. So basically the riser is just a hollow pipe, but it is the main reactor where actually the feed comes in contact with the hot catalyst, and the feed is liquid actually, by the way. It gets vaporized, and then it starts getting cracked as it goes along the length of the pipe. And as it comes out, then you have these cyclones, which actually separate the catalyst from the gases. And these are what you see here is a two-stage cyclone. So basically, the gases enter the eye of this cyclone, the catalyst falls through, and the gases then go into a second cyclone, so that we actually improve the efficiency of separation of the catalyst from the gases. And the products then actually go into the fractionation section, while the catalyst drops into this particular vessel, what is called as a stripper, where we inject steam. The idea behind this is that when the catalyst drops down, it still has a large amount of hydrocarbons, which is actually trapped in the inter particle area, interparticular volume. And so we need to strip those hydrocarbons out. This catalyst is a powder. This is neither an extrude, neither in the spherical form that we discussed earlier. So this is like a powder. It is not like the talcum powder that you use, but actually it is like a spherical powder. And I'll try to bring that catalyst here and show you. So this catalyst then actually goes through the standpipe. This is called as the spent catalyst standpipe. And there is a valve here, what we call as a slide valve, which actually helps to control the flow of this spent catalyst. This is called as a spent catalyst because now it has coked up because of the reaction which happens in the riser. And this catalyst then goes into this vessel, which we call as a regenerator, where we have air being blown in. This catalyst would come in at something like 480, 490, 500 degrees Celsius, depending upon at what temperature you want to run the reaction. Okay, so it is always around 500 and higher. And that catalyst comes here, and then you, at that temperature of about 500 degrees Celsius, the air helps you to burn off the carbon from the surface of the catalyst. And that heat which is generated here is absorbed by the catalyst. Again, you have these cyclones which actually help to remove the catalyst from the flue gases. And the flue gases, which essentially now contains carbon monoxide, carbon dioxide, sulfur dioxide, which is sulfur which is deposited on the catalyst, as well as steam, because and then the rest of the nitrogen, because some amount of hydrogen also comes in, which gets converted to H2O, plus actually the rest of the nitrogen, which comes along with the air. So this flue gas is actually like almost like 78% nitrogen, and the rest of it is CO, CO2, steam, and SO2. And that is actually then sent to the flue gas treatment section. While the hot catalyst, the catalyst which gets heated up because of this exothermic reaction, now passes through what is called as another standpipe called regenerated catalyst standpipe, and the flow rate is controlled through this slide valve, which is called regenerated catalyst slide valve. And that actually then continues its journey. So once it actually comes in, it gets carried up, fluidized up by steam. This is actually called as a fluidizing steam. And then once it meets the feed, it gets vaporized, and then the journey continues. So basically, we have two reactors. One is where actually the real reaction takes place in terms of cracking. This is a highly endothermic reaction, because any heavier molecule, if you want to crack to a lower molecule, and there is no hydrogen here. This is zero hydrogen. We don't put any hydrogen. So this is a highly endothermic reaction. The entire heat that is provided for overcoming this endothermicity is by this hot catalyst coming in. And then by the time it goes up, it gets cooled down to whatever reactor temperature you're operating. So it might go down from 700 to something like 500. And this delta T of 200 degrees Celsius is kind of made up by the regenerator, where actually the carbon, when it gets burnt, generates the heat, which is enough to actually heat up the catalyst in order to sustain the endothermicity of the reaction. So basically, the reactor and the regenerator are completely heat balanced. The endothermicity, the extent of endothermic heat, let's say if you require something like 100 million kilocalories per hour of endothermic heat, that is exactly same as 100 million kilocalorie per hour of exotherm, which is generated in the regenerator. And the vector, the heat carrying vector between these two is the catalyst itself. So the catalyst actually carries the heat from the regenerator to the riser to provide that endothermicity. And then actually the spent catalyst along with the carbon goes back into the regenerator to actually burn off the carbon. So as you can see, this is really a very innovative technology. And coming to think of it, that it was invented way back 70 years ago, it is quite a marvel. And actually, they're moving around solid material, from one vessel to the other in a continuous way. In fact, a particular particle of catalyst would go through this entire journey in less than 10 minutes. And that is what actually I wanted to show you before, because at that moment in time, it was quite premature to talk about it. But you can see that in good old times, when this reactor was also not in fluidized mode, there was no riser. This was also in a fluidized mode. This was also in a fluidized mode. The catalyst residence time in the reactor was like 30 to 120 seconds. With riser cracking, where actually the catalyst particles they shoot through the riser at very fast velocity. It's of the order of 15 some feet per second at the bottom to 60 feet per second at the top. So it is pretty high, actually, almost like 5 meters per second at the bottom to something like 20 meters per second at the top. And the total time that is spent by the vapor is only about a couple of seconds in the riser cracking, while the catalyst might spend something like 5 seconds, 5 to 15 seconds. Because there is, of course, some back mixing, so the catalyst has more residence time as it goes through the riser because of its higher density. And the temperatures can go anywhere from 480 to 650 at the top, depending upon how you operate the reactor. And we'll discuss in great depth about process variables like riser temperature, etc. So you can see that there is a big difference. And as I told you earlier in this picture that, yeah, in this picture that the riser crackers started to come in late 70s and early 80s. Before that, it was all fluidized bed type of a reactor, no riser cracking. So this was actually a major breakthrough which happened, sometime around 1955, when this was much after the Shell actually installed the cracker in Chimbo. So the riser cracking today is the way it is done, with very short residence times of 2 to 3 or maximum 5 seconds in the riser. So in that 5 seconds, all these products are produced. Okay, in that very short time of 5 seconds, and and then you actually separate out these products into their components. So basically, to summarize what I just said just now, the hydrocarbon feed is brought into intimate contact with the hot catalyst. The feed is vaporized and cracked and leaves behind coke. The vapors and catalysts are separated in the reactor separator, and then it is stripped. The vapors flow into the separation section. The coke-laden catalyst is brought in contact with air, where it burns, where the carbon gets burnt, and you get hot regenerated catalyst, and that actually goes back into the riser, and the journey continues. So this is what we discussed. To get into some of the further details regarding the reactor regenerator section. So this diagram tells you, like this is the lift steam that we talked about. In fact, some of the operators use other than steam like cocoa naphtha, etc., so that they get more conversion and more yields. Feed is actually injected through actually injectors, and this is another piece of technology which has actually gone through quite a bit of development, and we'll talk about injectors later. And this is the total residence time that you have, 3 to 5 seconds into this riser. As you can see here, the catalyst and the hydrocarbon vapors that it comes out, you need to actually separate them immediately. Otherwise, if the catalyst continues to live along with the hydrocarbon, it will further crack the precious hydrocarbons into something which could be invaluable, not valuable. So this is actually these two cyclones, etc., that you see, and we'll talk about that later, is actually what is called as a riser termination devices. Here we have VSS. This is vortex separator system, which actually separates out the catalyst from the hydrocarbons, and the catalyst then drops down into this stripper where we have baffles, and we got steam coming in here at the bottom, which actually strips this bed of catalyst while still keeping it in the fluidized state. And this catalyst then actually flows through the standpipe through this slide valve into the regenerator. Here, actually, on purpose, I have shown you another configuration of the regenerator. This is actually a two-stage regenerator, the first stage and the second stage, because there's a large amount of carbon to be burned, and with two stage we can reduce the total amount of air that you may need. So basically the catalyst along with the carbon that goes into the first stage, where actually the part of the air we put in and part of the gases which is actually coming out of the second stage, they go into the first stage, where there's still some amount of oxygen left in the flue gases coming out of the second stage. And that actually burns off the carbon completely. And what you get out is something like, say, a flue gas at about 680 to 700 degrees Celsius. The catalyst after the first stage goes into the second stage, where you have fresh air now coming in, and that gets kind of burns off every gram of carbon on the catalyst. And this hot catalyst then actually comes into the riser back again. The numbers that you see here are typical. For example, as you can see that the reactor operates at a pretty low pressure. In fact, this is why actually FCC units are very useful, and they make more money, because any cracking reaction not only is endothermic, but also actually it creates extra volume, huge volume. So it is always beneficial to operate at low pressure. So you can afford to operate the reactor at as low as pressure as 2 bar. And why you're limited to 2 bar is because of the pressure drop in the fractionation section. While actually the regenerator operates at slightly higher pressure, so that there's enough pressure here to actually take into account the pressure drop in the flue gas treatment section. So this is how actually the two vessels are linked. As far as the control is concerned, as I told you, this is the spent catalyst slide valve, and this is the regenerated catalyst slide valve. This slide valve is operated by the temperature controller of the reactor, while this slide valve here of the spent catalyst standpipe is actually controlled by the level controller here. So this is how you actually keep the reactor regenerator under catalyst mass balance as well as heat balance. So actually the reactor regenerator is all about balances. Actually there are three balances which are pretty active, and we'll talk about in greater detail later. One is of course the heat balance, and that heat balance is maintained by this slide valve. So for example, if the operator wants to go from 490 to 492 degrees Celsius, and he punches in a change in the set point of the DCS, what will happen is that this particular controller will start opening this valve, so that more hot catalyst comes in. More hot catalyst comes in, the more will be the temperature here, the more will be the coke deposit. The higher the coke deposit, the more will be the air required, and more heat will get generated, and the catalyst coming in will be slightly more hot, and thereby actually it stabilizes to a new steady state. Similarly, when the catalyst comes out and gets deposited in the stripper here, the level goes up, and so this level controller will open the slide valve to let that extra catalyst come through. So basically this level controller maintains the material balance around this reactor, particularly in the stripper zone, by keeping the level constant. And similarly, this particular slide valve on the regenerated catalyst standpipe controls the reactor temperature, and it maintains a heat balance between the reactor regenerator. So this is, so this is actually as far as the reactor regenerator is concerned. If you look at the whole reactor regenerator, and put it into the complete flow sheet of a typical FCC unit. So now you can see that we were only concentrating in these two in the reactor regenerator, which is the heart of the process. Okay, and there are two things which come out here. So we get feed coming in and air coming in, but what comes out here is actually the reaction products, and what comes out from the regenerator is the flue gas. So what you see in this picture now is to how do we handle these two. As far as the reaction products are concerned, it is actually taken into a distillation column, very much similar to the atmospheric column that you had studied earlier. And similar to the atmospheric column, we have the side strippers and the pump arounds, etc., where we actually separate out all those products. The non-condensed material goes on to the condenser, well, actually, whatever gets condensed. You also have water here because we are putting steam all over the place, and not only from the bottom in the riser, but also in the stripper. So this water, all the steam actually goes here and then condenses at the top. So you have actually the water layer at the bottom and the hydrocarbon layer at the top. Part of the hydrocarbon is reflux, and then part of it is taken into the gas concentration section, which we'll talk about later. So as far as the regenerator is concerned, the flue gas which comes out still has, although you have two-stage cyclones here, that means first stage and second stage, but you still have very fine catalyst particles still coming along with the flue gas into what is called as a third stage separator. So here actually we create a cyclone. We have a vortex that we create because of which the catalyst gets separated out. Very, very fine catalyst particles, anywhere up to about 10 or 15 microns. And the flue gas, which is pretty hot flue gas, actually then can be used to actually generate power through a turbo expander. So the flue gas comes in and you can run a turbine on this flue gas to be able to generate electricity. Or you can have a direct couple your turbine to a compressor, which actually compresses air to provide air to the regenerator. Quite a few FCC units which are large in capacity, something like more than roughly about 3.5 to 4 million tons per annum capacity. There actually it becomes economically viable to put in a turbo expander. So you get flue gas and then you go through a turbo expander, or in other words, a turbine to generate power, and that power can be put into the grid or can be used elsewhere in the refinery or can be used to run a compressor, as you can see here. The hot flue gas still has large amount of heat, so we put it through a boiler. In this case, we call it as a CO boiler because there is some amount of CO coming in. So we combust that CO to CO2 and generate that extra heat to generate steam. And that steam is then used to generate further power, as you can see here, or actually used for running distillation columns, etc. And then the flue gas after the CO boiler actually goes into the ESP, the electrostatic precipitator, or actually flue gas, desulfurization system so that the sulfur dioxide is removed, and then you put the flue gas into the atmosphere. Uh, Actually, the FCC unit is the second largest contributor of carbon dioxide into the atmosphere in a refinery. The largest, of course, is the hydrogen plant. But there is almost like 8 to 10% of the feed which is actually burnt off in the regenerator in the form of carbon, and that actually produces significant quantity of carbon dioxide which goes into the atmosphere. So this is actually the full flow sheet of an FCC unit. I'll just repeat so that you remember. This is the reactor regenerator section that we talked about earlier. And we went into the great depth about how do you control temperature and levels and pressures, etc. And the reactor of gases, that the reactor products, they go into the distillation column, and I'll get back to that in a minute. And the flue gas actually goes into the flue gas treatment section, where it consists of essentially three things. Number one is actually a third stage separator to separate out the catalyst fines, and then into the CO boiler, where actually you generate, sorry, from the catalyst, from the third stage separator, it goes into, if required, and if technically and commercially viable, into a turbo expander or a turbine to generate electricity. And then the rest of the flue gas, which is still pretty hot, goes into the boiler. If there is CO, it burns the CO and produces steam, and that steam is then used elsewhere, while the gases are then actually further scrubbed to actually, or go through an electrostatic precipitator to remove catalyst fines as well as sulfur dioxide. Coming on to the distillation column, actually the one that you see on the right, this is the very simplified picture of this column. I didn't want to actually spend too much of effort here. Basically, there are three very important things to remember regarding this column. First of all, it is not called a distillation column, it is called as a primary fractionator, because there are many distillation columns which follow this. Okay, so there are many distillation columns which follow this, but this is the first one, which receives the product gases coming out of the reactor. So the reactor of gases, remember these are pretty hot gases, right? Depending upon the temperature at which you're running the reactor, these gases could be anywhere between 500 to 530 degrees Celsius, or even higher. And so, as I told you long time ago, and many times before that, that any hydrocarbon stream above 360 degrees Celsius can crack. So what we do here is that these hot gases are quenched by a very large pump around system that you see here with a cooler. What we do is that the slurry, which is actually the unconverted material, which is at the bottom, this is called CLO, clarified oil, in some refineries, or in American refineries, and also in Jamnagar, we call it as CSO, circulating slurry oil. And this slurry oil actually contains some catalyst fines. That is why it is called slurry catalyst oil. As slurry, I mean, circulating slurry oil. But actually, there is a large amount of circulation. What happens here? So actually, this reactor of gases, which is vapor, are quenched, and the condensation that we do is basically of the CSO, that is the unconverted material. So the gases, after quenching roughly at about 360 degrees Celsius, so we actually maintain this circuit in such a way that the bottom temperature never exceeds 360 degrees Celsius, 360. And so the gases rise up at 360 degrees Celsius. And similar to what we had in the crude distillation column, we have actually the pump arounds, by which actually we condense the kind of fraction that we are looking for. So the HCO gets condensed, and typically we have the steam stripper here to strip out the light fractions like we had seen before. And we have actually HCO, which is blended into the diesel pool. Similarly, actually, as the gases go up, we have LCO, and you can see this is the circulating reflux on the LCO. And this is the light cycle oil, this is the heavy cycle oil. Depending upon the cetane number of these two, we may actually put HCO into the fuel oil pool and not blend that with the diesel, because the cetane number of HCO would be definitely lower, because it has higher polynuclear aromatics as compared to LCO. LCO, this is actually something like boiling between 360 to 430 degrees. Something like that, in that range, at atmospheric pressure. And then you have rest of the gases going through. You actually can separate out heavy gasoline as well. So this is the pump around for that, and then you separate out the heavy gasoline with a reboil stripper. And then what happens is that the rest of the gases which go up, which are still uncondensed, and this could be the overhead temperature could be as high as something like 105, 106 degrees. That goes into a fin fan cooler and condensers. These are huge condensers at the top, where actually we try to condense as much as we can of course, the entire water gets condensed, and this is how we call sour water because it has a significant quantity of dissolved H2S. And the uncondensed gases go actually to the gas concentration section. So this is where actually so just to repeat, the reactor effluent, which is pretty hot, is actually quenched immediately as they come to the bottom of this column. And this is very different as compared to what you see in the atmospheric column. So this is one difference that you should remember. And then you have the circulating reflux, the circulating quench system, which helps to condense, not only condense the gases, but also to cool the gases. And whatever actually goes up is at 360. So you start recovering all the side fractions, what you saw earlier in that table, and whatever doesn't condense go to the top. And to just to complete the story before I finish, these gases. So from this reflux drum, you see two products coming out. One is the liquid product, and the other is the gaseous product. Okay. So we will trace these two. So what happens is that the gaseous product, they go through a two-stage compressor. This is actually why we don't have this compressor system in the atmospheric distillation column, because first, number one, the gases flow rate is very small, and number two, we actually take advantage of the naphtha stabilizer as well. But here the gases are pretty high because actually remember we actually went through a cracker. So these quantities are pretty high and it cannot be condensed, and we cannot actually operate this column at a higher pressure like we did the naphtha stabilizer. Because if you operate this at a higher pressure, the reactor would also have to be operated at a higher pressure, and that will actually not help in getting higher conversion rate. So essentially, we want to keep this pressure, this column at as low as pressure as possible, roughly about 1 atmosphere in the drum. So we need a compressor then. So it is a two-stage compressor. So the gas comes in and then it goes through a first-stage compressor, gets cooled. Whatever condenses out gets condensed out, and then the rest of the gases gets compressed again. Ultimately, everything gets collected into a drum, where actually this pressure that we maintain in this drum is about 15 kg, 15 bar, 15 kg per square centimeter. Some amount of water will condense out here, but still there are gases which are non-condensed even at 15 bar. And you can imagine that these would be gases like hydrogen, H2S, CO, CO2, etc., and methane, and some amount of ethane. So these gases actually will still contain some heavier hydrocarbons because after all, this is a single stage flash here. So this is actually sent into a primary absorber where we take the gasoline from the primary fractionation drum. This liquid actually comes from here. This is this liquid, which is actually the heavy gasoline absorption oil. So this particular gasoline is used here to absorb some of the heavier hydrocarbons which might escape along with this gas. And that actually is added back here. While actually the gases now, which relatively have no very little amount of heavy hydrocarbons, is again actually subjected to another absorber. This is called secondary absorber, where you put an absorption oil, which is uh, which is um, part of this material itself. And this actually goes back into the primary fractionation column, that is the main column. While these are the gases, then actually are sent into the fuel gas header in a refinery. So this has still a pretty high calorific value because it has hydrogen C1, C2, C3, C, and a little bit of C4. Very not large amount of C4, but at least C1, C2, with a little C3 actually. And these this bottom liquid then actually comes from the bottom and actually gets stripped in a stripper, in a reboiled stripper, because this would have some dissolved gases, and those gases are actually put back into the feed to the drum before the condenser. And this stripped liquid now is basically containing LPG and gasoline. So this is like a naphtha stabilizer or debutanizer. where you actually separate out the LPG. So here this particular column operates at pretty high pressure at about 12 to 15 bar. So you actually separate out the LPG from the top and the gasoline from the bottom. So this is how actually the whole separation takes place. We will stop here, and actually when I begin next time, I will actually